how much additional income would we have to give that person to make them as well off under the new prices as they were under the old prices. And from a practical sort of political point of view, this is the number you want to know if you want to get this person to vote for the proposed change in policy, to vote for the increased gasoline tax. Okay, so this is a useful number to know. So we can compute this thing. I'm going to talk my way through this first, then I'm going to draw a picture, and then I'm going to give you an equation. Well, we've got an equation here. I'll justify this thing or relate this thing to the graph. So look at this. So let's imagine the original level of prices is P, and we're going to achieve some level of utility U. Then we know the total expenditures for this person are going to be E of PU. So that's if they have a level of utility of U, this is how much money they need to spend. Now, prices increase to P prime, or change to P prime. And the question is, what's the change in income which allows that person to achieve the same level of utility U? So this U and this U are the same numbers. And so this is the new level of expenditures required to achieve a level of utility U. And so these are expenditures. This is something in dollars. This is something in dollars, or some other sort of value. And so the difference between those things is how much you have to give to a consumer to compensate them for an increase in gasoline tax, for example. Okay. And that quantity is called the compensating variation. Okay. Is the usefulness of that clear? Probably. I should give you an example. Okay. All right. So let me do that. So let's. There's a couple different graphs I can use to think about this. Let me give you the complicated one first. So the complicated one I've already started to draw for you. Let me take this example of the gasoline tax. So I'm going to think about a commodity space involving gas and other goods. Or you might want to think of this as travel services, something people like. So other goods. So this is other goods are in dollars. Okay, so we've got some initial indifference curve. This level is a level of utility U, or you can make it U star. We have an initial set of prices that pin down demand for gasoline and other goods. And so this is our initial, this is P. We have now what we're going to do is increase prices. So we're going to double the price of gasoline, let's say, just like we did before. That's going to give us a slope of this thing, which is twice as large. That's not quite right. Like that. So this is P prime, and this area under here is the new budget set. Now, as we observed already, if this is your new budget set, given the increase in gasoline prices, there's no way you can get to this point. That's no longer feasible. So, I'm sorry, I'll make this P prime. So, at the new prices, how much additional income do we need to give this person to get them back to the original level of utility? So this one here is Y divided by P2. At the new prices, we can increase Y. How much do we have to increase it to get them up to here? Up to a point on this indifference curve. Oh, I like this. I see people going like this. So yeah, we'll take the new prices, P prime, keep the slope the same, and just do a parallel shift in the budget set until we hit the original indifference curve. And so that's going to give, see if I can draw this. It's going to give us a point that looks like this, roughly. And P2 hasn't changed, so this intersection up here is, let's call it Y prime divided by P2. And so this distance tells us almost how much we need to change. This distance is Y prime minus Y divided by P2. So the compensating variation, in this case, will just be equal to the income change we need from this, which will be equal to P2 times Y prime minus Y. So CV here is the compensating variation. So notice the story here. The story is, for some reason, we want people to consume less gasoline. So we double the price of gasoline by imposing a tax. That reduces demand. In this case, it reduces demand a lot. But now people really hate the policy because they're much worse off with the new high prices than they were at the old. So at the same time, we increase relative gasoline prices. We give them money so that they can get back to the original indifference curve. That makes everyone so they're just as happy as they were before. But now they're consuming this amount of gasoline. Let's call it X1 prime instead of this amount of gasoline, X2 prime. Now, notice what we've got in this construction. We're still on the same indifference curve here. So what is this difference in terms of demands we work with? I think I heard the answer. What is it? Second? It's the difference is the substitution effect. And it's coming right off the difference in the Hicksian demands. We're holding utility fixed in effect to get the demand here and the demand here. We got the second demand by compensating the consumer for the price increase. And for that reason, what I've been calling Hicksian demands are often also called compensated demands. So that's a term you might have encountered in the textbooks, for example. They're the same thing. This is why they're called compensated. Yes? Oh, I'm sorry. That's a typo. Thank you. I meant X1, not prime. Thank you. Yes?
Why the compensated variation depends on the price because it was not increasing?
Oh, just because the units here are in terms of units of the other good. So if this is measured in dollars, then the price of a dollar is 1, so we're done. But if this is cups of coffee, then the amount of income you have to give me is measured in, I need to turn it into cups of coffee on this axis in effect. Yeah. Okay, so this distance then would be measured in 5,000 cups of coffee. To get an income, I need to multiply by how much a cup of coffee costs. Okay, is that clear? Okay, I've got another picture to draw for you that I think is certainly less messy. So this diagram is in demand space. So we're going to have quantities of demand X1 here, and we're going to have prices here. And so let's think about the Hicksian demand. And the Hicksian demand here is going to be, so I'm going to draw H, or it's really H inverse, as a function of prices and some level of utility U star. Okay, so that's just the Hicksian demand curve in the backward Marshall demand space. Okay, now I want to think about how this is related to compensating variation. And the trick I'm going to use here is to go back and recall Shepard's lemma. So remember, Shepard's lemma says what? It relates the Hicksian demand function and the expenditure function. How does it do it? That's exactly right. What's the actual formula? Do you recall? Yeah. It's just it's a simple one. So it's that the Hicksian demand, so Hi of P U star, is equal to the partial derivative of the expenditure function, P U star, with respect to prices. So it's equal to that partial derivative. Okay. All right. So I want to note this thing here, and then I want to think about applying the fundamental theorem of calculus. And so that gives me a different relationship between expenditures and the Hicksian demand. What is it? I'm just going to integrate both sides. So it follows from this that the integral of hi p u star with respect to p I is equal to expenditures. Okay, so that's it. I'm just going to take this thing, integrate. I get back the expenditure function equal to the integral of the Higgs demand. Okay. You guys are smiling because you're made happy by the fundamental theorem of calculus. Okay, that's great. So let me express that graphically. What's this graph? What does this integral look like on this graph? Yeah, so it's the area. Remember, the axes are backwards. So if this is, let's say this is the initial level of price. Let's say this is the initial level of prices. So let's call this P1. Then all this area under the Higgs demand curve is just equal to E of P U star, or I should say P1, I guess. Okay, so this area is that expenditure. I'm just integrating over P1. So from 0 up to P1, that area is the expenditure function. Okay, so we're thinking about the price of, is that clear? We're thinking about the demand for gasoline now. We're going to double gasoline prices. So we've got a new price up here. I said I was going to double it, so here's P1 prime. What's the expenditure function now in this graph that allows us to keep the same level of utility? Right? How can I figure out what the expenditure function is in this graph? Same trick, I just need to integrate up to a higher level of prices. So total, if price of gasoline is P1 and I want to achieve a level of utility U star, I need to integrate over this area. And so this whole area is equal to E of P prime U star. Okay, so this big area is equal to this, the small area is equal to this. The compensating variation is equal to the difference. E of P prime U minus E of P U. And so that difference here graphically is just this little area. It's the difference area between these guys. Let me shade this for you. So this is the compensating variation, which is equal to E of P prime U star minus E of P U star. It's the answer to how much income you have to give somebody to compensate them for an increase in price from P to P prime. Okay, let me ask you a question. Suppose we have let's think about the gasoline example for a moment. And I actually happen to have here some data on gasoline demand for the U.S. So this is per household. And so here's a little time series of gasoline demand. And so for the average U.S. household, during the week ending, the 9th of September 2010, used a little bit less than 3.4 gallons of gasoline per week. That's the answer. This is in gallons per week per household. Okay. So this is how much consumers households demanded during that period. I also have some data on prices. The dates don't match up perfectly, unfortunately. But the price at the pump at the end of what I have here, 2010. The price at the pump at the end of on 13th of September 2010 was $2.72 at a 10. This is measured in pennies here. So the average price of gasoline, retail price of gasoline at the pump was $2.72. So this is an average. You should remember this is an average for the. Well, first of all, it was a year ago. Prices have increased a lot over the last year. So this is an average of the entire U.S. And gasoline California has the most expensive gas prices in the country. So it won't match very closely what you see here in Berkeley. Okay. Anyway, so these were average gasoline prices a year ago. If we doubled them, then I'd like to be able to say something about how much we need to compensate U.S. consumers. And so here's a question: the average household consumed 3.4 gallons of gasoline. If we doubled prices from 272, so let's figure out their expenditures. Actually, somebody with a calculator could help me. We have a phone. Do you have a calculator on that? So the expenditures in 2010 per household were 2.721 times, what do we say, 3.387 gallons per week. So what's that equal to? So $9.21 in weekly expenditures for the average U.S. household on gasoline 1 year ago. Okay, if we double gasoline prices for this household that was consuming $3.83 this amount of gasoline in gallons, then at the old level of consumption, what would expenditures be? Well, so just multiply this by 2, so I guess that's that. Yeah, I can get it in my hand. That was $18.42. Okay, right, so if we double prices, leave consumption fixed, then we get an expenditure of $18.42. So here's a question: why isn't the compensating variation for the average household just the difference between these $9.21? Yes. Okay, so the answer is because the demand for gasoline changes. What's going to happen to it? Okay, and so when your prices increase, demand will decrease. So should compensating variation be more or less than the difference between these and $9.21? Okay, very good. So it should be less. And so what's the logic? Yeah, so Hillary says that's right. To stay on the same utility curve, you don't have to take into account the fact that they still are going to be purchasing the same basket of goods. Let me draw that picture really quickly and I'll let you go. Do it here, I guess. So one way we constructed our compensating variation. Introduce this graph. No, I got rid of it. Was to think about gas and other goods. I've got an indifference curve. I've got an initial level of, whoops, that's not tangents. I've got an initial price. I've got a doubling in price of gasoline, and I've got a compensating variation. So we said that this is where people would be demanding gasoline. They're on the same indifference curve. This is quite different from what we would need to do if we just made it possible for them to buy the original bundle of goods. If we did that, what we would do is we'd find the budget line which passed through this original point. So parallel to this, something I don't know. Right. So I'm trying to draw this as parallel to that. That would give us a line something like this, which is just a lot more than this. So that would make it possible for them to buy this original bundle. That's feasible now. That would get them to this utility function, but it's a lot more income than they need to achieve the same level of utility. Okay. All right, questions about that? Okay, let's stop there. I'll see you Thursday.